Air Force Research Laboratory's Air Vehicles Directorate has been working on a solution to aileron reversal for some time. They call it the Active Aeroelastic Wing Program.
I like to liken aeroelastic wing to being able to allow you to have a weight-competitive, higher aspect ratio wing than a designer will use.
This particular aircraft is a modified FA-18 aircraft that exhibited some problems early in its development phase, which made it ideal for this research program.
The test jet was named the X-53 and modified to test the active aeroelastic wing concept.
With active aeroelastic wing technology, is all about learning to use the leading edge surfaces in addition to the trailing edge surfaces. When we deflect the leading edge surfaces up, we can create a force near the leading edge, which causes a twisting moment in this manner, causing the wing to twist like this. And that wing twist is advantageous, and we can actually exploit that.
Active aeroelastic wing technology integrates existing control techniques with a novel structural approach to enable a higher aspect ratio, more aerodynamically efficient wing platform.
We've completed all of our flight research. We're still in the process of analyzing data, but we have matured the technology to a point where we think it's ready to be applied to a next generation air vehicle.
An awful lot of people are involved in a project like this, and so it's quite a rewarding experience to see it fly.
When a project like the Active Aeroelastic Wing Program enters the testing stage, many components go through rigorous testing in facilities like this.
This is the Trisonic Gas Dynamic Facility, or TGF for short.
And though incredibly powerful, this is one of many types and sizes of wind tunnels the Air Force Research Laboratory uses.
Basically, we're set up to run anywhere from 0.3 Mach, which is subsonic, all the way up to Mach 3.0. We have a 2-foot by 2-foot test section, so we can bring in different pieces of the model, whether it be a wing or an inlet. And yes, we bring in stuff that's state-of-the-art, building the technologies that future folks in the Air Force are going to get to maintain and work on and actually see we're developing it here. So it's kind of cool.
Another Air Vehicles Directorate program in the midst of extensive testing is one geared toward creating the next generation of unmanned aerial vehicles.
A platform that can do the air-to-air surveillance, also provide surveillance to the ground, and also to do that over very large quantities of airspace and ground space.
What AFRL is striving for is really an unmanned aerial system with a design and capabilities far different from today's unmanned aircraft.
The sensor suite is actually embedded in the wing. It's very high-tech in terms of its shape and also in terms of the technical challenges that we face. And one of the more challenging ones is the fact that you won't see airplanes that currently fly that have these very, very long tapered wings that are also swept. We're doing a lot of wind tunnel testing, particularly at NASA. The benefit is the increased capability that we can give in the surveillance arena to the warfighter of the future.
The Air Force, like any large corporation, sets goals and timelines for all its efforts. And that can be a challenge when it comes to research and development.
Science is an iterative process where I have an idea, I pursue it, it doesn't work, I go back to the laboratory, I push it a little bit further, I take it out to the field, explore it a little bit more. So it's highly nonlinear, and it's interactive between the person in the laboratory and the applications. So of course that makes marching to timelines very difficult. We have tremendous successes, though, that we've demonstrated.
One example of those successes is the laboratory's response to a top priority request from the Air Force Special Operations Command.
This particular project started with General Woolley, the commander of AFSOC, sending a request to our commander saying that helicopter brownout is his highest priority urgent need.
Helicopter brownout happens during landings in dusty, sandy environments. And when it happens, pilots are pretty much blind to their surroundings.
And doing a helicopter brownout was pretty much the scariest environment imaginable.
Major Grube is one of the pilots the Special Operations Command provided to help with the brownout research program. During 2 tours in Iraq and 1 in Afghanistan, he faced many brownout landings.
There's really no margin for error, so once you sit up on the approach, you're really just setting yourself up for a controlled crash. Once you're engulfed in the dust, you're in the landing attitude, and you just continue until you hit the ground. And just about every other day, we were damaging the helicopter in some form or fashion.
It took only 3 months for the cross-discipline team of experts involved to come up with a possible solution, one that proved very successful during testing over the following months.
And so the solution we came up is, in my opinion, very elegant.
It's an incredible technology. Really, they've taken an 11 megapixel camera, take a picture of the landing zone, use the aircraft's navigation system, which for us is extremely accurate, takes a picture, maps it out onto space, and then overlays your position onto the landing site.
Uses an IR flash. It is designed to be night vision vehicle compatible.
You know, we were seeing guys' shoelaces at one football field distance at night.
AFRL is also working on mid- and long-term solutions to the helicopter brownout problem, with programs focused on finding a way to see through the dust and new aircraft designs that reduce or eliminate brownout situations altogether.
It's still going down.
We have some of the most important problems that a scientist or technologist could imagine working on.
And when it comes to aircraft, some of the most important work is in developing craft that will fly farther and faster than ever before.
I have to admit, my personal favorite is a program called the X-51. The X-51 is a program intended to demonstrate flight in what we call the hypersonic regime, that is flight in excess of about 5 or 6 times the speed of sound. Now, to put that into some perspective, a jet fighter will fly at up to 1.5, maybe twice the speed of sound, Mach 2. What we're interested in is a range of aircraft and spacecraft that can operate in the atmosphere in the speed range of approximately Mach 6, Mach 7, Mach 8.
The X-51 concept is based on the use of a supersonic combustion ramjet, or scramjet. And though scramjet technology has been around for some time and gone through much ground testing, only limited flight testing has been done.
In the year 2004, NASA flew a vehicle called the X-43 that was powered by one of these scramjet engines. It set an air-breathing speed record of almost Mach 10 times the speed of sound. But it only did that for 10 seconds, and it did that burning hydrogen fuel. X-51 is the next logical step. It will demonstrate flight of several minutes, and it will do that burning a hydrocarbon fuel that's much more practical to use in the Air Force. It is pioneering a new class of weapon systems. Also, it's opening up a new class of vehicles that could get us into space using a more airplane-like approach. The Air Force, in many ways, was founded, first and foremost, as a technology enterprise. One could argue the reason that we're a separate branch of the service, separate from the original Army Air Corps, was a recognition of the value of science and technology in our mission.
The active aeroelastic wing, nanotechnology, and biomimetics, they all have the sound of science fiction, but each is a present-day technology. And there are only 3 examples of the many technologies Air Force research laboratory teams are using every day to create new tools and capabilities for today's military men and women in uniform. I'm Master Sergeant Daniela Marcus, and this has been Recon.